Set a good example then. All right, for good behavior. So I want to talk about using data to discover and governing equations and models just from time series recordings. I'm going to really focus on two things: model discovery and also this idea of thinking about how to generate coordinates. This is all done with my colleague Steve Brunt, who's another faculty member at the University of Washington. I won't talk about measurements and sensor, although that's a very important part of this data collection process. So here it is. Here's the goal. You have a state space variable x. It's a dynamic system, whatever you're measuring. It could be neuroscience, it could be fluid flow, it could be some kind of mechanical process. It's governed by some dynamical equation, which has some parametric dependency, could even have some stochastics. It's time dependent. But what you have access to is measurements. You have a measurement at certain time points, t of k. And by the way, you don't necessarily measure x directly. You measure something of x, right? X oftentimes is going to be a latent variable, and you're going to measure some point of this. So you have snapshots of a system, and here's the goal. Given the data, y, can you tell me what the measurement model is? Can you tell me what your state space is? Can you tell me what your governing equations are, the parameters, right? And this is all given that you're taking noisy measurements. So first of all, this is an impossible problem. It's called ill-posed, right, mathematically, but we do it anyway. How do we do it? You make assumptions. What we do mathematically, we call assumptions. We call these things constraints or regularizers. That's it. So that's what we're going to do, is constrain and regularize this to get actual solutions of this from data. It's early. It's pre-9 o'clock, so we're just going to stick with ax equal to b for a while. So first part of this talk, all it is ax equal to b, okay? But here's the thing we're not doing a very good job of teaching is this is ax equal to b for us. Massive, there's no n by n's. N by n's don't exist. Those are like unicorns. In real data science, your data is either tall, skinny matrices, short, fat matrices. You're massively over or under determined. So these are either no solutions or an infinite number. So right away, even when you get this ax equal to b, you've got to think about how I'm going to get the solution. And by the way, here's just some MATLAB commands that will get you ax equal to b solved. You hit it and you go, what's the problem? I got a solution. So all of these are making assumptions on regularization. So this is going to be the key thing, is you're going to make some kind of regularization assumption. And what we want to do is make regularization assumptions that are relevant for physics modeling. All right, so first of all, let's ask, what could the right-hand side be? What we're going to build is a library. You're in a library now. You could go grab all the science books, and you can look at all the equations we've written down, from Maxwell's equations to quantum mechanics to classical mechanics. Look at all the equations we have in our bodies of knowledge that we've developed so far. And you say, put all those terms in a library. You could have diffusion. You could have dispersion. You could have nonlinear terms. Whatever you want to do, put it all in here. This is a library of potential physics terms, in some sense. This is the matrix A in ax equal to b. And each row of this is a measurement in time. So I measure the state space, and I can construct all these library terms from a measurement to build this library. That's the matrix A. And typically, this is a tall, skinny matrix. Okay? The right-hand side B is going to be the derivative of my time series, because I have x dot equals some right-hand side. So if I give you the time series, you differentiate it. So you have x dot equals a times some loading coefficient for this. And what I want to do is promote sparsity. Because if you look at any of those physics books you pick up, or engineering books, they all kind of fit on one line. Maxwell's equations, Schrodinger. It's like there's a few terms, 2, 3 often. In the particularly brutal case, you might have 4 or 5, or it runs over the next page. But the point is, it's typically, out of all these possibilities, there's only a few that matter. So all I'm just going to do is say x equal to b, promote sparsity. Okay? And by the way, I'm not doing this with lasso. Lasso is actually not very good in practice. So here it is. I'm going to give you an example. Lorenz, I take time series data. I make this time series data. So this is a little example. So I give you x, y, and z. I just give you time series data. You can differentiate that to produce this side, which is b. I give you the library, and up to this is up to polynomials degree 5, and then here is your loadings for these things. So ax equal to b. And what do I want this thing to be? Sparse. if I do a backslash in MATLAB here, it's L2 regression, it's least squares, it will say every term is important, which is a very like West Coast thing, right? Everybody's important. Versus, actually, I just want to say a few of you are important, right? So it promotes sparsity. Those are the non-zero elements, and in fact, it pulls out those terms exactly. Now, here's the beauty of this. How many parameters do I have? 7. So it's not like a neural net where you train massive number of weights with all these parameters, hyperparameter tuning. I have 7 parameters that come out of this. You can generalize this to PDEs. So here I'm going to give you a canonical set of PDEs. KDV, Berger, Schrodinger, NLS, KS. I can generate data from all of these, and I can actually discover those models. So if I measure fluid flow, I can discover Navier-Stokes. Okay? So that's the idea behind this, is that you can take the same framework, just load the library now with spatial temporal type terms. So this is assuming that you kind of know no physics. You just take time series data and you recover physics. Now, I think this, and by the way, we started there, but we've really moved towards more here, which is you never approach a system you don't know anything. You actually know a lot. The problem is what you know doesn't quite match up with what you see. So oftentimes, the idea is that there's some discrepancy. So the idea is to say, instead of discovering everything from scratch, you basically start off saying, well, I actually know quite a bit. By the way, in the previous framework, if you knew there were terms that were in the physics, you just put them in the left-hand side. You can include it part of B. It's trivial to include physics that you already know in that AX equal to B. But now we're going to say, OK, well, I have this model, and I look at my data, my model, they don't quite match. So you could do some Koopman filtering here. But the idea here is to say, well, why don't I take that data discrepancy and try to learn a model for what's wrong? So I'm going to give you this as an example. Double pendulum. Let's take the Platonic idealization of a double pendulum. You can write down the equations, F equal ma physics, and then you say, I'm going to tell this little cart here what the governing equations are, and say, go, you can move around and stabilize the pendulum in the upright position. And it does that with your physics model, and it can't do it. Why? Because actually there's nonlinear frictional forces both in the wind and also inside of the joints themselves. But if you take the time series data and say, like, learn the discrepancy, it will say, OK, I'm going to learn that your physics isn't quite right. Let me make a correction to it, learn a little nonlinear correction to that, and now I have the right physics. I didn't have to learn all brand new physics. I just had to learn the pieces I was missing. So I think this is kind of an important future for us in terms of discrepancy model, because really it's heading towards this idea of a digital twin. Right? So if I can take a system like this, here's my digital twin of this robot arm, I can write down all the Platonic physics of this, in other words, the idealized model, and you look at what this does versus this, they don't match. Partly because the real physics here is not just your standard F equals ma you wrote down. There's nonlinear things that you've missed, frictional forces, things like this that you need to put in, learn them, now your digital twin's going to pick that up. Okay? So this is one way to go about this. Everything I talked about was AX equal to B. So let's switch gears. Maybe that was a dumb thing to do. We're learning nonlinear physics. What if instead I switched to saying, maybe I should just learn a better coordinate system? Maybe in a better coordinate system, I would just do better way to express my physics. So here's the idea, and this is back to Bernard Koopman. So maybe some of you have heard about this Koopman theory, which is kind of an important area in dynamical systems these days, because it is about the discovery of a coordinate system where essentially you take a nonlinear dynamical system, finite dimensional, and if I can get the right functional forms of g of x, in other words, I'm going to work in a space which are functions of that state space. If I can pick the right g of x, I can make this thing linear. Now here's the beauty of linear dynamics. I can write down the solution on pen and paper, and I'm done. Forecasting, pen and paper, everything. Now here's the problem. 1931, Koopman has no computer. So it's an idealization. If I found a unicorn, look what I could do. Right? That's kind of where we are with this. And in fact, this was picked back up, and the dynamic mode decomposition was one way to approximate this. And what we're trying to do is make this better. Now let me just show you this in practice. Here's one example. This is like a simple ODE, Boyce and DePrima level. Here's the nonlinearity. It's a nonlinear dynamical system. Or I could write it in these variables, y1, y2, y3, if I define them this way, and this thing's just linear. So what I did is I found a better coordinate system because now the system's completely linear. Okay? Write down analytic solutions, do anytime forecasting. And there's usually, this is a little bit simple in the sense that most of the time you run into closure problems, but we've actually shown where you can actually do this and work it out directly. Here's another famous example, Berger's equation. If you're in the PDE world, this is one of your famous nonlinear PDEs. What you have is nonlinear vectoring terms from diffusive regularization. It's a nonlinear PDE. People very interested in the 50s. And then Cole and Hoff independently derived this transformation, which gets you from U to V. So there's a couple of things here. So first of all, the V is more parsimonious, 2 terms, and it's linear. What we'd like to do is figure out how can I actually do that. In practice, so we're going to try to use neural nets to do it. So this is going to be a very targeted use of a neural net. All the neural net has to do is learn an embedding, a coordinate transformation. That's it. I'm not letting it do anything else. Okay? So I want to learn from an input space to an output space. Let's just do the pendulum. It's a 2-dimensional system. A lot of people solve really hard problems with neural nets. I dare you to come after it and go after the pendulum. That's a hard problem. People think we've solved that. We haven't. A lot of your neural nets will break on the pendulum. How do I know? Because I failed a lot on the pendulum until I figured out kind of how to maybe do this, which is I want to go from an input to a new space. You know what I want to have happen in this new space? I want the dynamics between y of k to y of k plus 1 to be linear. So I want to learn this representation to a linear space. And then if you start training this, and by the way, this is work with Bethany Lush, who was a former student and postdoc, now at Argonne, you fail. And you fail, and we failed for a long time, and we were feeling stupid. But then we figured out, oh, it's obvious why we failed, and I brought back my graduate education from the 90s on asymptotics. Nobody seems to learn this anymore, but I thought it was wasted knowledge. But see, this is my notes I photocopied in. This is how excited I was. Check it out. Let's just take pendulum with a little nonlinearity. This is the first correction. This is a Duffing equation. And what happens with that nonlinearity? Nonlinearity does 2 things. It shifts your frequencies, and it creates harmonics. So if you try to build a linear map in 2 dimensions, and this is going on, you'll fail. Why? Because let's look at the dynamics. Here's a spectrogram. As I increase the amplitude, here is your frequency shift. Here's your harmonics. So notice I need to use the whole range of frequencies to do this. So if you're going to do a neural net, you can go to high dimensions and it will learn it easily. But what you've done is you've basically told your neural net, build a Taylor series representation. You haven't really learned physics. To keep this down to 2 dimensions, what you also have to do is then parameterize that embedding. So if I learn a second network where I learn that frequency dependence, I now can keep this thing linear where the linear map is parameterized by the frequency. Then I have a fully linear embedding of the nonlinear pendulum. So this is one way to think about Koopman coordinates, try to make things linear. And now we're going to try to combine them. And this is just came up on the archive. This is Kathleen Champion. She's actually defending on Monday next week. She's fantastic, and she started putting this together, which is, how about at the first part of my talk and the second part of the talk? Let's put it together. Because here's the deal. You're going to measure a system, and suppose here's some pendulum. You know, in your head, you think theta, theta, dot. Those are the right coordinates. But I gave you a GoPro, and you took pixel space pictures. The pixel space doesn't know anything about theta, theta, dot. So the first thing you got to do when you take your measurements from your sensors is, it's not clear you have the right state space measurement at all. So your first goal is you better find the right coordinate system, because if you don't find the right coordinate systems, you will not get a parsimonious dynamical model parameterized by 2, 3 parameters. So what we're going to do is basically take this neural net idea, take my measurement space, in this case it was a pixel space, map it through a coordinate transformation. All it needs to do is to learn a coordinate transformation. And instead of making this linear now, I say, you know what, let's relax that a little bit and let this be now this sparse identification model, this AX equal B I told you about. Learn from me a parsimonious representation of the dynamics, minimally parametrized. It can be nonlinear now, and then come back out. So this is combining the best of both worlds. Find me great coordinates, find me a great model, and in fact, I guess the way we think about it now is you have to do this. If you're going to get good models, you have to do good coordinates. So I take the Lorentz again. I project each direction into some spatial mode. So this is actually my data. I give you this, and I say, go find the model for me. So now it has to both find a coordinate system and the dynamics, and it actually can do that. So here's the actual model. Here's the discovered model. One thing that's interesting, it gives you a representation of Lorentz, which is slightly different. But this is a linear transformation away from this. We do that, we get here. So I guess here's the bottom line, conclusion. If you're going to do this model discovery, this allows you to do this parsimonious representation, minimal parameterization. It gets us back to physical terms you can interpret and generalize. That's the best shot you have, is you have the minimal parameterizations, but you also have to simultaneously discover a coordinate system that goes along with that. So I'll stop there. Okay.